really nice to be here with you again. My name is Andra Somesan. I'm a senior solutions architect at AWS Romania, based here in Bucharest. And together with my colleague Radu, we will walk you through how you can get started, as Timothy said, from zero to production LLMs with EKS, KRO, and GitOps. And just to give you an overview what we're going to discuss about today, we will start with an AI architecture on Kubernetes overview. I know you're all experts, but it's good to have an overview of what we're going to discuss. Then we'll be introducing some EKS capabilities. And out of these EKS capabilities, we will cover them specifically for platforms. Then we'll dive a little bit deeper into KRO templates, and of course, the most interesting part of the day, the demo of the talk, of course. So we work at AWS, that's clear. So we meet with customers every day. The customers that we see choosing Kubernetes for GenAI are typically those who have already standardized on Kubernetes as their operating model in the cloud. If you've already built a platform on EKS, you've already got many of the capabilities you need to run production-grade applications, like disaster recovery, cost visibility, deployment automation, observability. And you also have access to all the underlying resources and primitives that you need, from compute to networking to storage and security. And this is a skill set that you already have within your organizations. It's a technology you are familiar with, and if you already host more traditional workloads on EKS, you can get to market faster, you can build faster, and you are just extending your existing implementations in hosting these models. And of course, running those GenAI applications, like building agentic AI applications, running inference, or even fine-tuning. And here is an overview of how this infrastructure looks like. We are going to walk through all the core components that you need to deploy models to EKS. From the cluster capabilities you need to provisioning the GPUs your model will run, storage solutions for how to store the model, and how to expose that to an endpoint. How to auto-scale that, and of course, how to implement observability into this solution. And if you look here and follow through the steps, you need first to provision that compute, right? You will need some GPUs in the cloud. Then you will need to run your containers. For that, you will need to download some models from some model registry and store them in a storage so that you can easily fetch them. After that, you will load the model into the GPU memory, and of course, you will have to think about auto-scaling as well. And before moving on to the other side of this picture, running on GPU from running containers, you will have to have VLLMs on those machines, and to run everything in clusters, you will also need Ray to control everything. Moving further, after you've built all this, you will like to share what you build with others, have an endpoint that you have to expose, and other users, applications, AI agents interacting with that endpoint that you just exposed. And of course, it's always important to have this observability added into the picture and monitor everything. But that's not all, right? I mean, that's complex, but that's not all. Looking at even higher scale, like going above and looking what's happening, this is the AI architecture when using open source frameworks, because you will need that AI gateway, and you most likely will work with different model providers, from OpenAI to Amazon Bedrock and all the others. And to do that, you have to have an AI gateway, like in this example, like LLM, Kong, or Portkey, but there are many other ones. The model serving engine will be VLLM. And when we're talking about building, what you will build is mainly agents. And to build those agents, you will need frameworks to build it. You can use either Strands agents, LangGraph, Crew AI, or other that you prefer. For your agents, you will need VectorDB or very, very good data sources. And here are a few examples of those as well. Talking about observability at a higher scale, you will need LangFuse, for example, which is a popular tool of choice. And here are a few other examples. Of course, your agents have to integrate with and easily work with MCP servers. And to make it easier to test or just to experiment with it, you can add some UI frameworks as well. And of course, to overcome all these challenges and bring them, make them better, this is nothing new, right? We already know about platform engineering. And platform engineering is what most successful organizations use in implementing these solutions. And why is that? Is because first, they increase velocity through enhanced developer experience. That's easy. Second, they reduce friction by establishing well-defined paved paths that everybody just goes and follows. Third, they ensure security, compliance through all the built-in guardrails. And fourth, they improve simplicity by creating these meaningful abstractions. If you don't have to know about it, you won't know about it. You will just use it and make what you want to build faster. And of course, instead of spending months building everything from scratch, what if there was a more efficient way to overcome these challenges? The answer lies in implementing a comprehensive GitOps-based solution that encompasses 4 essential components. First, full automation. That's crucial. Eliminating manual intervention and reducing human error, enabling you to scale. Second, we need these built-in self-healing capabilities to maintain consistency and provide simplified, centralized resources that reduces all the inconsistencies that can come up. Third, the solution must offer declarative, immutable configurations complemented by an intuitive user interface that's easy to use and reduces the cognitive overload. And fourth, comprehensive observability and auditability. These features are essential to maintain the security and compliance, enforcing these security standards. And if we're talking about EKS specifically, this is how Amazon EKS looks like. You have Amazon EKS cluster, and you have the managed control plane that's running in an EKS account of AWS. And you have your own customer account that runs the self-managed OSSs, the cluster resources, and all the other AWS resources that you might use in that account. And what we did, we saw that Argo CD, AG, and KRO are really valuable for our customers, and we included them in as managed capabilities. Because first, Argo CD, you need some standardized battle-tested GitOps engine, right? Offering Argo CD as a managed add-on reduces all the operational burden, ensures compatibility with EKS upgrades, and gives you a supported path to GitOps, an easy one without do-it-yourself setup. AG deepens the EKS control plane for everything. So basically, instead of going outside your EKS cluster and doing commissioning resources, you can stay in your familiar environment, stay in EKS, stay with the commands that you're familiar with, and build other resources. And KRO is the glue layer. AG lets you manage AWS resources. KRO lets you compose them into golden paths. KRO gives platform teams the tooling to build internal developer platforms without writing any custom operators. And beyond having standardized on Kubernetes as your platform, you can choose EKS for many other core reasons. Kubernetes provides a rich ecosystem of open source tooling for AI and ML in particular as well. The community is constantly innovating and progressing Kubernetes to support GenAI workloads. EKS offers native integration that works seamlessly with other AWS services for observability, networking, or storage. And you have granular control over your infrastructure, allowing you to right-size resources, leverage spot instances, and efficiently manage your compute. This level of control can lead to significant cost savings. With EKS, you have full control over both your data and your infrastructure. This allows you to deeply performance tune your applications and ensures that your systems are tailored precisely to specific requirements. Lastly, Kubernetes enables consistent deployment, whether you're running in the cloud, on premises, or at the edge. This flexibility ensures uniform performance and reliability across any deployment scenario that you might have. And with that, I will pass it on to my colleague to get into the interesting part. Radu?
Thank you very much, Andra. Good afternoon, everyone. Good afternoon, my name is Radu, I'm a colleague of Andra at AWS, and moving forward I'm just going to show you a proposal of how you can use these tools, the Argo CD, ACK and KRO, to kind of define a new layer of abstraction for AI platforms. So Andra already mentioned with EKS, right, what AWS is doing is taking a lot of the complexity of operating Kubernetes by managing the control plane, giving the customers just the operational burden of the workloads themselves, right? When we talk about AI inference, we've seen how complex it can be, but now we can see that using KRO, we can actually raise this level of abstraction and give the users simply what they need to do to provision some models and use them. And using these tools, I kind of created this architecture. Is a very opinionated architecture with the open source frameworks that Andra just mentioned. And it's just the essentials, right? So we have the core infrastructure there with the GPU nodes. So these are nodes in a Kubernetes cluster with GPU attached to them, which are managed by VLLM, which is the inference engine itself. And then we have Ray for scalable inference, right? This is a Ray cluster. And then we use Light LLM specifically as an AI gateway. We use Langfuse for observability, and we have OpenWeb UI to just expose a chat interface to the users. And Light LLM can be hooked. Let's say it can have multiple providers of models, whether it's Amazon Bedrock, OpenAI, Azure, Google, whatever, and obviously it can expose our own models hosted in EKS. And how do we simplify? How do we create this additional layer of abstraction? By using the KRO template. So KRO, what allows us to do is actually bring all those complex components that we need in inference. So the Ray cluster, the VLLM inference engine, some configurations, registering this new model into the gateway, and so on. We would need to either work with each of them individually or to automate it. And this is where KRO templates comes into play, right? Because what we can do is we can define a custom resource in Kubernetes. We will call it inference endpoint. And within this custom resource, we package all those individual components. So this is how the KRO template actually looks like. And if you see here, we have, I don't think you see a pointer, but basically we have a specification which kind of defines the model that we want to run, minimum and maximum replicas, because we are making this auto-scalable based on demand. The worker memory and CPU to define to make sure that what the node that we provision is enough to run that model. And then we have the resources, right? So these specifications, these are the only attributes that will be exposed to, let's say, a model user, whether it's a development team that wants to experiment with a model, whether it's a data science team that wants to experiment, and so on. And then within the resources, we see that we define all the resources that make up the deployment of an LLM, right? One of them would be this platform configuration. This is a simple config map in EKS where we store some configurations. The other one would be light LLM register. So this resource is nothing but a custom script which actually calls a light LLM API and registers this model automatically in our AI gateway. Then we have the big part, which is the Ray service. This is the Ray cluster, which we actually use to deploy that model in. It includes VLLM, and this is auto-scalable, so we can scale those Ray workers. And then we also have a resource, which is basically a service in AWS. This is just a CloudWatch log group, which we use to actually collect the logs from that model. But it can be any service within AWS through the ACK. So it can be an S3 bucket, it can be an RDS database, it can be an EC2 instance, whatever service in AWS, we can describe as a native Kubernetes resource in EKS through this ACK. And once we have this template all set up, basically this is what a consuming team will need to deploy a model. So rather than go through that complex architecture that Andra showed, where we need to provision the GPU nodes, and we need to register that model in VLLM and in Ray, and we need to have the image for Ray and VLLM to pull it from a repository, and then we need to register this model in AI Gateway to expose it, all that is needed is a YAML that defines this inference endpoint, the custom resource that we defined in the KRO template. So the experience will look like this. Instead of having like 12 steps, the developer can actually just look into Hugging Face, identify the model that they want to run, then create this simple YAML and commit it to their Git. Argo CD will automatically deploy that. And now let's try to do exactly that within a demo, hopefully. And just so here we have a Argo setup. So all the platform actually is managed through Argo. But here I'm just showing you the workloads, right? So Light LLM, all the other applications are also managed by Argo. But this is just the workloads that we want. So we have two teams. This is a KRO template that defines the teams. So as a platform team, we can onboard other teams, which again, can be data science teams that want to experiment with new models, can be developers that want to deploy their own models. And we can actually define what we want for each individual team, as in limits of how many GPUs they can consume, or limits of how many tokens per minute and how many requests per minute they can use on each model, right? And we can create those teams, and then we will see we automatically plug these teams into Light LLM, which is the gateway, and enforces all of these regulations. But what we want to see now is how we can deploy a new model, right? So we see we already have a Hugging Face model here. It's a small LLM from Hugging Face, small LLM 3. And we have here some sort of dashboard. I'll try to make it a little bit more visible. So this is a dashboard that shows our EKS cluster. It runs on version 135. This is a node group, which contains basically all the necessary critical add-ons to run this cluster. And then we have 3 Carpenter node pools. Carpenter is, think of a cluster autoscaler, which manages the worker nodes in that cluster. And we have created here 2 node pools by Carpenter. One of them is GPU inference nodes. So these are nodes that will have a GPU attached to it, and where we can provision nodes that are large enough for 1 or multiple GPUs. So this will be dedicated GPU nodes. However, we can have smaller LLMs where maybe it's not, I mean, it's a waste of resources to have this small LLM on an entire resource with an entire GPU. And we want to use time slicing, that we can share 1 GPU to run multiple LLMs in parallel. So we have GPU shared node pool. And what we want to do now is to have exactly this experiment to see what the experience would be for a developer, right? So they just go to Hugging Face. Let's say they want to experiment with a new model. I just picked Gemma 3 1 billion because it's a tiny one. And there is also included in this solution, there's this recommend instance helper script, which basically we can use with any, okay, just a second. Okay, this is going to be tricky, sorry about that. Are you with me so far? Yes. Thank you so much. Okay. So Gemma is a gated model on Hugging Face, then I needed to set up the token. So what this script does, this helper script, is actually looking at the model and recommends an EC2 instance that would be large enough to accommodate the model. And you have different options, so it looks at the GPU memory that you would need, and it gives you different options of instances where you can run it. Based on the dimension of the model, it says whether it can be shared. So it's a small enough model that you can use one instance, a shared instance, to run multiple similar small models, or it needs a dedicated instance. So in this case, we can see that it's quite a small model, so a shared one is fine. And then this helper script automatically generates the YAML for that inference endpoint that we create with KRO, right? So we can see here that we have the model. It's Gemma from Google. It needs one GPU. It is shared. Then we have some calculation of VRAMs. So Carpenter will know what sort of instance to provision for it. So what we need to do now is simply to copy paste this one. And then to push the model. Okay. So now if we go back to Argo, usually this would not need any intervention, so Argo would actually sync it automatically, but I think there is like a 3-minute wait. So I'll just do this manually. And now we should see the process kicking in. So what is happening behind the scenes is that Argo actually, after the push, is starting to provision this model. So because we said that this is a shared model, we will see that the model will be provisioned on a pre-warm instance, right? So we already had that instance running where we have one CPU with 4 slots. And just to give you an idea what is happening in the backend while this is loading, because one of the benefits of KRO is not only that we can, let's say, abstract this complexity, but we also can codify some of the best practices in operating LLMs. For example, how do we avoid the cold start? So if you look at this top layer, what usually happens when we deploy a model, we need to provision a new node. Let's say we have a dedicated node where we need to run this model. We need to provision it with Carpenter. This might take 40 to 50 seconds. Then we would need to pull in an image of this node, right? So if we use Ray cluster and VLLM, that means that we need to pull that image on the node. This is quite large, it's like 30 gigs. So we need to wait for that image to be ready. Then we need to actually load the model, so either download it from Hugging Face, load all the weights of the model in the memory of the GPU. And then we need to basically expose it in the AI. And there are some, let's say, good practices, recommendations, how we can shorten all this cold startup for VLLM models. One of them is to use SOCI, stands for Seekable OCI. And basically, it's a way to load the image in parallel by doing lazy loading of the image itself. right? So we will pull only the layers that we need for that image to be able to have a faster startup for that big 30 gig ray image. So this is kind of the middle point. And then even more, we can actually even remove completely these two steps, the one for provisioning a node, if we keep a node running, just as a warm-up node. And then if we use EBS snapshots for keeping all that image. So what we can do is we can actually store the entire 30 gigs image in an EBS snapshot. When we provision a new node, we instantly attach that EBS snapshot to the node, and then the image is there, we don't need to pull it, right? So with these mechanisms, and of course there is always a trade-off between keeping an instance warm and keeping an EBS snapshot, and you have to pay for those resources. If you need faster scale-up, then maybe you want to use these methods rather than a cold start. And this is something that we implemented here as well with our model, and hopefully it will be provisioned soon. Yeah, we have it running. So that means that we can see it in our API gateway, AI gateway, of course, and it's been already deployed. And we can even experiment. So now we also have Gemma here. I can say, hey, who are you? So this would be like the typical, like just an experience of an end user who has a chat interface. And we can see that we can now compare all the two. And obviously it's just a starting point, so it's just to see how you can leverage Argo CD, KRO to kind of build your own platform. And these are just some choices of Light LLM as a gateway and this open web UI as interface, but it can serve multiple purposes. And it's not as, I think the key point here is that we're not trading off, let's say, complexity of managing the AI, moving everything to Argo and KRO and ACK, and then we have to manage Argo, KRO, and ACK, and we're just trading complexity of AI with complexity of these tools, right? We need to move the complexity here, and then AWS manages these three capabilities: Argo as a managed service, KRO as a managed service, ACK controllers as managed, which means, again, that we can provision any resource from AWS as a native Kubernetes resource. So it's just a starting point. Look into it. A great way to run models on EKS, especially since everyone is looking now into running smaller models, more specialized models, training and fine-tuning the models. We all use the commercial ones, I'm sure, but this is a way to have more control over the models in a optimized way, both operationally and more cost-effective. That's it.